Hello, everyone. Welcome to this webinar. It's a great pleasure to announce a partnership with Deeplite. And this is the first webinar we are going to host today. It's about a tool called Neutrino. It's an AI-driven optimizer for cloud and edge. So today is about how to get started with Neutrino on CMC AI Cluster. It's my pleasure to present the presenters today. So we have Davis. Davis is a co-founder and CPO of Deeplite. And Yasser is a principal software engineer, Deeplite, and myself, I work for CMC Microsystems. So let me give you a high-level overview about this partnership. So the goal here is to make Deeplite's powerful AI software platform, Neutrino, available to researchers across CMC Design Network, National Design Network. So the benefit to the user by using Neutrino on CMC AI Cluster is to have access to a broad range of platforms, including RISC-V, GPUs, FPGAs, and even path to silicon. We will be hosting a community version of Neutrino on CMC AI Cluster, so people can benefit from the speed up on different accelerators, mainly GPUs and FPGAs. And we will continue supporting the community that join this framework by delivering webinars, training, workshop, and maintaining a community forum where people can discuss about their advancements using this tool. So a little bit intro of CMC Microsystem. So we are not for profits. CMC is founded in 1984, and its mission is to manage the Canada National Design Network. And next slide, I'm going to talk a little bit about the Canada National Design Network. And we do this by providing an infrastructure for innovation in different disciplines, including microelectronics, photonics, MEMS, nanofabrication, AI and machine learning, and quantum computing. So the National Design Network, or the NDN, is a large Canada-wide collaborative project between 67 universities and colleges to connect 10,000 academic participants with over 1,000 companies. And the main goal here is to enable research and development projects to design, make, and test micro and nanosystem prototypes. We measure the outcome by the number of publication awards, patents awarded, the collaboration with industry, new startups, trained HQP moved to industry, and annually we engage with 1,275 professors and their collaborators. And to summarize the products and services that CMC offer, it's summarized by CAD, Fab, and Lab. Under the CAD banner, we offer state-of-the-art software for successful design. These software are accelerated in high-performance cloud-based servers, and this with a secure distributed private cloud. And we offer with that user guides, PDKs, application notes, training material, and courses. Under the Fab banner, which consists of providing simple access and reduced cost for working prototypes. And this consists of MPW, which stands for multi-project wafer services through a global supply chain. So in microelectronic, we offer access to fab down to 12 nanometer, and we offer also fabrication services to of silicon photonics devices, microelectronics, mechanical system, MEMS, and nanofabrication. Along with expertise from CMC engineers in designing and packaging and assembly services. Lab consists of tools for test and demonstration. These are platform technologies such as FPGA, GPUs, high-performance CPUs in the cloud, test equipment loans for short-term needs, technical contract services, and other products and services in that area. So we offer these products and services by engaging with global partner and offering a worldwide industrial supply chain. So we engage with partners in North America, Europe, Asia, Australia. And the main goal here is really enhance researchers' capabilities by accessing CADs, Fab, and Lab products and services. So Currently, we provide over 500 CAD tools. They are in the cloud, accessible in a secure manner. People can just log in and use one of these tools. And currently, we have over 5,000 users annually using these tools. So back to the subject of this webinar, since we are talking about artificial intelligence and machine learning, and I think everybody is familiar with these concepts, but I would like to highlight here is that deep learning is a hot area since the last 10 years in machine learning, and it consists of multi-layer neural network that learn from vast amounts of data. So AI currently transforming many industries, and you see a lot of opportunities by integrating AI solution, especially at the edge, so really mobile devices. And we witness explosion of ecosystem of tools and platforms. So let's look at the key drivers that advance the AI. So first of all, great availability of large data sets containing more training examples. You can go to ImageNet or you go to Kaggle and you have large data set for different area, and you can start using them, training your neural network. This is the first driver. The second one, novel algorithms, including new models, open source machine learning, such as TensorFlow, PyTorch, and these are accelerated in GPUs, FPGAs, and custom hardware, such as tensor processor to train deep neural network. So as of today, why do we need better AI hardware? So here I try to summarize some data from OpenAI, and this really summarizes the evolution of deep neural network over the last 10 years, and this trend is continuing to the future. So let's look back at 2012, the first date, the first revolution of deep neural network. And the first one was AlexNet, which was able to win the ImageNet competition. And we have progressed from AlexNet to AlphaGo Zero, which was able to defeat the world champions in Go. So in order to get from this level of performance required by AlexNet to AlphaGo Zero, we had to increase the performance by 300,000x. And if we followed Moore's law over the span of this period, we could have obtained only 10x. So we really need to bridge the gap going forward between the level of performance we need and the level of performance that we could have obtained from Moore's law. So the world is moving towards specialized hardware, so innovative hardware that can accelerate deep learning, and optimization tools to meet the exponentially growing demand for compute. And I think the neutrino that we are going to introduce today play a very significant role in making deep neural network available at every edge device. So let's look at the AI hardware matrix, 2x2 matrix. You have the training and inference. In the cloud, the training and inference can be accelerated in GPUs, TPUs, or FPGAs. And the inference at the edge is a very hot topic today because of many advantages. First of all, it offers real time. It can be used in autonomous cars, and you really need to have very fast response from your neural network. Compute latency, you don't need to depend on the connectivity. Data privacy, you don't need to share your data with the cloud to do processing, and connectivity and bandwidth limitation. So, but this comes at a cost to process or to enable AI at the edge. You require a high computational complexity, memory footprint should be very small, and power consumption should be very small in order to be able to do that. So here I summarized some of the products and services of CMC to support AI. The first one is not related to AI, but it's a CAD compute cluster to accelerate all the CAD tools that we have. And the second one is really more equipped with the tools and the frameworks to do AI inference and training in the cloud. It's an FPGA GPU cluster. And here I give more details about it. It's a multiple nodes. We have nodes that feature 2 FPGAs. We have nodes that feature 2 GPUs. And we have some nodes that feature 1 FPGA, 1 GPU. And these are the latest FPGA GPUs today. The GPU is a V100 Tesla, and the FPGA is the Alveo U200, and a complete software stack to do machine learning or deep learning using TensorFlow, Caffe, PyTorch. Coming soon is a hardware cluster that also that supports a lot of users, concurrent users at the same time. This is for real-time inference and training that demands high efficiency at low power consumption. And this is a particular cluster. It's composed by 4 of these ultra high performance servers, and it is based on ARM architecture. So going back to how to use the CMC cloud design environment, it's very simple. You need to select a particular node and reserve it. By reserving it, you can mention the number of hours you need, and you can manage it by extending the duration of your reservation, delete it or connect to it. When you connect to it, you have 2 ways to use it, either using desktop or SSH. And this slide summarizes a very simple environment based on Anaconda, where you can just activate Anaconda and activate your favorite environment to do machine learning, either PyTorch or TensorFlow. They are both supported. And you can run TensorBoard and look at the results of your training. So this is a kind of extremely high level description of what you can do with this cluster. But now we're going to dive into the details with the Deeplite presentation. But before that, I would like to mention that we have an upcoming workshop in May 4th. So the attendees of this webinar will have, we will send you the link to register. But this workshop will focus on AI acceleration, challenges and opportunities, and we are interested in different topics, including inference in the edge computing, software stack, benchmarking, running edge AI application on RISC-V, and latest trends in AI chip design and commercialization, and also applying AI to different areas, especially to the EDA, the CAD industry. So I will stop sharing my desktop, and I will hand it to Davis, who will be talking a little bit about Deeplite.
Perfect. So thanks so much, Yassine. Actually, I think Yasser, if you could throw up the slides in a second, that's perfect. So thank you everyone for taking the time today for this webinar, and thank you so much to Yassine and CMC for having us. We're very, very excited about the potential for this. So as you saw from the summary of the AI cluster, a lot of power, a lot of accessibility in terms of some compute, for particularly that first quadrant Yassine mentioned, that training in the cloud. And in today, in the demo we're going to get into, we're going to really talk about how we can bridge, the different quadrants we're referring to. So from the cloud training, to cloud inference, but especially that really interesting quadrant of edge SoC inference. And in particular at Deeplite, what we are really focused on is how to optimize these neural networks so that they can go from large and too slow to small and fast enough to deploy on all the different hardware and the different places we want to and can deploy them. So to kick things off, my name is Davis. I'm one of the co-founders of Deeplite. I'll keep this introduction very, very short. I think the focus for today is really on what Yasser is going to present with the demo and how we can actually use Neutrino. But to give a quick background on Deeplite, we're a Montreal-based software company. We were founded a few years ago here with the team, predominantly, venture-backed here in the Canadian ecosystem, and we're really proud to be partners with all the amazing names you see here, like Mila and ARM, and especially most recently CMC. So that's really the focus for today on the AI cluster and how Neutrino community, which we're just releasing in this month. And so for everyone joining today, as Brian mentioned at the beginning in the chat, please feel free to throw any questions. I just shared the link in the chat for the registration for Neutrino community. We'll come back to it at the end as well, but that's there, and we really encourage you and look forward to you to getting set up. So quickly on Deeplite, as I mentioned, it's all about AI. It's all about optimizing AI. We really are independent of applications. So what we mean by that is in the different quadrants and different spaces that AI is commonly used, we really optimize deep neural nets to be faster, smaller, more efficient across these different domains. And that's exciting because whether your application is object detection for a vehicle or image classification for a smart camera or speaker ID, these are all problems that deep learning can solve and are all problems that optimized deep learning can be deployed and solved at the edge. And that's really what we focus on here. And to be more specific, there's really two things we can talk about today. We'll see a demo for sure with compression. If you have time, we can get into the throughput mode as well. But there's two things we can optimize for, basically. We have a neural network. We want to deploy it on some hardware, and we can either make this hardware and the network run faster. We can have higher throughput. We can have faster response times. We can optimize for that, which is super exciting. And I think really the sweet spot, especially, and we have a lot of deployments and a lot of exciting experience around here, is the compression side of things. Taking a neural network that needs the memory, needs the compute of a GPU or high-end CPU, and making it able to run on an MCU or an SoC, or even multiple networks on a GPU or CPU. That's another big benefit of compression. So again, just to kind of summarize the context here for where Neutrino fits in, as you guys are probably familiar with, we have some training infrastructure, which is becoming more and more standard, accessible, and robust, like the CMC AI Cluster, and that's where you can design and train, and that's where it lives, and that's that. But we want to deploy, and that gap I think Yassine was referring to, is really getting to any target hardware and doing this in the most efficient and automated way possible. Those are really the two key things, and hopefully that'll be one of the great takeaways from this demo, is the automation side of things, how easy and how near instantaneous we can be with this process. And the whole point of this process is to bring AI to the in-memory or at the very edge of computing. So as this typical memory hierarchy diagram shows, what we really want to do is take the deep learning out of the higher bandwidth, but farther removed from the source of data storage, like in cloud, of course, and bring these neural network models to the very edge of computing. And that's where size is the big challenge. And so with Neutrino, what we're going to really focus on today is how we can break through this barrier and create, through an MLOps structure with the cluster and with Neutrino, smaller, more efficient neural networks. So on that note, I'm going to hand over to you, Yasser. And yeah, thanks everyone for joining.
All right, thanks, Davis and Yassine. So my name is Yasser. I am a principal software engineer at Deeplite. Thanks everyone for joining. And to pick up from where Davis left, so basically, yes. So Neutrino is basically you can think of it as a black box that you put into your deep learning pipeline with the sole objective of optimizing your deep neural network, right? So you have if you're on a CMC cluster, you design your network, you do some training, and then eventually you pass your model and dataset to the Neutrino black box, and then you'll have an optimized model as an output, and then you can continue business as usual, where you can just deploy your model anywhere you want. The only difference is it's a lightweight version of this model. It's an optimized model. And as Davis mentioned, by optimized, we mean optimized for size, basically compressed, or for latency. So it's a lot faster to run inference on for edge devices or in the cloud. And to give you a more like a high-level architecture of our of where we fit into the deep learning stack. So basically, Neutrino is basically what we call. So we have two main products at Deeplite, right? So the first product, which we're going to be doing most of the talking today, is Neutrino. And basically, what Neutrino is basically it's a content-aware optimizer. And what that means is that we take your neural network, deep neural network, different model, regardless of the type of the model, classification, object detection, or a custom model, and we optimize it. We optimize it through either compression or latency mode, as we said, and regardless of two things. So this is agnostic to the Neutrino itself, the engine. It's agnostic to both the framework which the model was developed in, so TensorFlow, NNX, PyTorch, and it's also agnostic to the platform, the target hardware platform where it can basically run the inference on. And the other part that we do at Deeplite, it's basically called platform-aware optimization, which basically is what's represented by the black box here, the blue box, the Deeplite RT, which is the Deeplite runtime environment. And the purpose of Deeplite RT is to be able to run quantized, very small quantized models like 2-bit, 4-bit quantization quantized models on very small edge devices, microcontrollers, and stuff like this. So what we're going to be focusing our talk today is about Neutrino, and basically this is the box that this box represents the kind of the usage, how do you currently use a Neutrino, and the architecture of the different parameters that we need to pass to it. So typically what you need to pass to Neutrino is your model and your data set and some constraints, right? So how much are you willing to sacrifice in terms of the accuracy in order to gain optimization? So what we call this the delta, and the mode of the optimization, is it compression or latency mode? So compression mode, we're gonna, as you mentioned, we're going to be focusing about getting your model size smaller to fit on a smaller disk size, and as well as some other parameters like deep search. And basically what deep search mode does is that it consumes your delta, which means that it tries to optimize the model as much as it can, as long as we do not, like within the normal range that we're trying to respect for the delta provided by the user. And the target mode is means as soon as we hit any, as soon as we have, like, a smaller or a faster model within the delta range, we just stop. Obviously, the deep search takes a bit longer time to execute, to train, I mean. And then the other part is the precision, whether we basically want the target hardware is FE32, FP16, or a quantized version int8, or 4-bit or 2-bit, and so on and so forth. And then eventually what you get based on the different configurations and user input is an optimized version of the model. And as we said, by optimized, it means smaller model if you're in compression mode, and faster response time, lower latency if you're in latency mode, right? And we won't get into much, it's outside the scope of the call today to explain exactly the internals of how Neutrino work, but just to give you a teaser of what we actually do. Basically, as I mentioned before, Neutrino is a content-aware optimizer, which means that it modifies the architecture of the model itself by having by replacing it with, like, what we say an approximation of the provided neural network. And what we mean by this is that we use different techniques such as neural network search and design exploration with the sole purpose. Right now we're talking about the compression mode, so with the sole purpose of replacing these sub networks, if you will, with lighter or thinner versions of the networks. And when we say lighter or thinner versions, that mainly means fewer parameters, fewer weights, right? It does not necessarily mean that, less channels or less number of layers. But that's the whole idea, is that basically what we're trying to do is that we're exploring different sub networks, if you will, and we're trying to see which to look for, the best sub networks that need to be replaced, so that we have the optimized version of the neural network while maintaining the accuracy as specified by the user constraints. And just to give you, this is basically an example, a few examples of what Neutrino did achieve with a few of the models across different model types. So for image classifications, we have a lot of improvement. As you can see in the size, for example, if you check for VGG19, we have a standard data size, the model size is 80 megabytes. After Neutrino, the output was 2.16 megabytes, so almost 37x improvement. We also have a significant reduction in the number of flops, floating point operations, which means we reduced the computational complexity. And all this while maintaining, while basically the delta was 1, which means that we're within 1% of loss of accuracy. And you can see other examples as well. For segmentation, for example, we were able to achieve, like, for UNet, we're able to achieve 63x improvement in terms of model size, 47x in terms of number of flops, and the accuracy drop was 0.01%. And these are the names of the data sets. We're going to share the slides with you at the end, of course. And so this is just to give you, like, a taste of the output of Neutrino and one Neutrino can do in the compression mode. So let's okay. So enough talk. Let's go ahead and start with the demo and see how we can actually use Neutrino, how easy it is to use. So first, to get started with Neutrino, the way we deliver it right now, it's delivered via two things: via a standard Python wheel, pip package, or a Docker image, right? And as Davis and Yassin mentioned, we're going to be releasing a community version soon, and which means that everybody will be able to, like, sign up and obtain a community license and download and install the Neutrino and use it. Right now, the docs are not available. The documentation is not available online yet. It's going to be as soon as we have the community version released. And basically, the first thing is that we need to do is to install. So right now, for the purpose of this demo, we're going to walk through the installation of the pip package. So if we log into one of the CMC servers, like using SSH, as Yassin mentioned, we're going to start by just simply creating a new virtual environment, like the same way you do. You can use whatever virtual environment manager you use. We're going to use PyEnv, but you can use Conda or just a pure Python virtual env. So basically, we're going to use PyEnv to create a new virtual environment. Let's call it demo, and then we're going to activate it. Okay, and so here, the first thing that we need to do in the installation. So as explained, Neutrino itself, the Neutrino engine itself, it's platform agnostic piece of software, which means that it has nothing. It's not tied to a specific. Framework agnostic and platform agnostic as well, so, which means that it's not tied to a specific hardware nor it's tied to a specific deep learning framework. So it's not tied to PyTorch or TensorFlow or anything like this. The engine itself, right? So the first thing that we're going to go ahead and do is we're going to update the pip package just to be on the safe side, and then we're going to go ahead and install Neutrino. As I said, right now the packages are not publicly available, so we're going to have to enter a username and password to provide them. Once we have the community version, there's no need to do this. So the first thing is that we're going to install Neutrino engine, and then the second step is basically we're going to install for the purpose of this demo the Torch extension for the framework. We also have the TensorFlow extension, but it's not as ready or up to date yet as the Torch one, and eventually we can add other extensions like ONNX and potentially other types of backends. And the idea here is that basically that most of the optimization techniques and the core code we have is in the engine, and the framework extensions are really simple and thin implementations of specific tasks and functionalities in the framework itself. So we did install the engine itself. It went through without any issues, and then we're going to go ahead and install the Torch extension. And then the last part of Neutrino, this is optional. We don't need to install it, but for the purpose of this demo, we will, is what we call the Neutrino Torch Zoo. So basically, the zoo is just a zoo of models and data sets. So pre-trained models and data sets. And with the community edition, we're going to release this as open source so that other people can go ahead and contribute. And our goal is to have like a very comprehensive zoo that spans across different types of models. Like right now, we have a lot of classification, object detection, segmentation models. And the idea is that all of these models and data sets on the zoo right now are basically have been tested with Neutrino. But you don't have to actually use Neutrino to be able to use the zoo. You can basically use it as just a model zoo, and you can use it as totally outside basically the context of Neutrino. But right now, for the purpose of this demo, we're going to do a demo on ResNet 18 C400 dataset. So this is one of the supported, the provided models in the zoo. So basically, the zoo also is installable via pip. It's a pip package that we need to install. And then once the zoo is installed, we're just going to go ahead and the next step should be setting the license. So as we mentioned, in the community, once community edition is released, you're going to be able to, through your sign-up page, obtain a license key, and then you're just going to have to export it as an environment variable like this one, before eventually being able to use Neutrino. So now that the zoo is being installed, so as I mentioned, the zoo itself is going to be open source, and we're going to allow contributors to go ahead and provide their own pre-trained models. And the idea here is that we're going to go through a very simple classification example, and we can just go ahead and get it from here. So let me show you the code piece of this example. So basically, as you see, this very thin piece of code, apart from all this fancy arc parsing stuff, this is really Neutrino entry point. So this is what Neutrino, this is how easy it is to use Neutrino. All you need to do is just run one entry point, neutrino.run. That's it. And basically, what you need to provide is the framework type. In this case, it's going to be a Torch framework, your data set, and the reference model. That's it. In case of standard classification task like the one that we're exploring, you don't need to input anything else. Just the data set, the model, and of course your configuration, which basically include things that we saw on the slides earlier, the level of optimization that you need to do, level 1 or level 2, whether or not you want to enable the deep search mode, and of course the optimization mode, whether it's for latency or for compression. So that's pretty much it. And let's go ahead and give it a go. So basically, we're just going to do a dry run. And basically what this dry run option means is that, basically what this means is that we're not going to, because as we said, part of how Neutrino works, okay, sorry, it's Delta. Yeah. So basically, a part of how Neutrino works is through a neural architecture search. So we do different searches through subnetworks and replace them. So part of all these, while exploring the search space, we have to do a lot of retraining and fine-tuning to the newly produced models. And basically, what the dry run option means is basically that we don't really need to go through the full training. It just basically means we stop at the first epoch and terminate the training, so that otherwise it's going to take a while to finalize. And we can see here, and as we said, we just basically here the delta is 6, which means that we want to optimize this model, ResNet 18 on C400 dataset. We want to optimize it, and we allow for 6% drop of accuracy, which means that the target basically accuracy that we can allow for is about 70%. So because our baseline is 76% for ResNet 18 on C400, and basically what we allow for is we want to have an optimized model. Here we told it you want to have an optimized model, compressed model, and we allow for basically a drop of 6% in accuracy. And here, the first thing, the other so this is going to take a couple of minutes probably to finish, even with the dry run. Without the dry run, it's probably going to take I don't know, like a couple of hours or so, I guess. And I want to talk about the profiler. So this is another cool part of Neutrino that we're going to be open sourcing with the community version. And basically, what the profiler means, what it does is basically it profiles your model which means that it provides you with a lot of interesting metrics about your network. And the thing that I want to stress is that Profiler is a totally independent piece of software from Neutrino itself. Yeah, it's called Neutrino Profiler, but we use it in Neutrino as a third-party library. So basically, that means that when it's available, developers and engineers can use the Neutrino Profiler to provide their own models, and they can get interesting insights on their network. Things like the model size, the computational complexity, number of flops, the memory footprint, execution time. You can also get a few interesting statistics and metrics on the layer-wise information. So you can get a lot of information for each single layer of your model. We have a set of standard or predefined metrics in the profiler. A few of them are tailored to the compression basically mode, and the others are tailored to the latency mode. But you can add your we made it also very easy to contribute to add your new custom metrics to the profiler. So as we can see here, the dry run is finished, and basically it went through a few steps of optimization, like doing the proper search for smaller networks. And here eventually you have the result of the optimization. So as we see, the optimized model, the output model it's 70%, so it's about 6% less within the ballpark of what the user basically entered. The model size is basically went down from 42 megabytes to 9 megabytes, almost 4x enhancement. The computation complexity is also enhanced by more than double, which means that the number of flops were reduced. The number of parameters are also basically reduced significantly. They went down by almost 4x. So this is the value in millions. So from 11 million to 2 million parameters, weights, and biases. And the memory footprint also is basically optimized. And basically, the difference between the memory footprint and the model size is basically the memory footprint is what you actually use for need from the RAM for computation, for multiplications and additions. And even though we're running for a compression mode, even the execution time or the inference time is a little bit enhanced by almost 20%, 19%. Okay, and eventually, after all this is done, your model is exported into PyTorch JIT format, as well as on an X model, and also in your code here, you get the native PyTorch model as a return here to the function as a return value to the entry point of the function call. So yeah, so this is right now how easy it is to use Neutrino. A couple of more things I want to mention. Here we only basically went through a very standard classification task, and we run it in a single node environment, in a virtual environment, isolated virtual environment. As I mentioned, we also do provide Neutrino as a separate Docker image. And one of the main reasons we do this is that we also support distributed training. And this means that you can run Neutrino on a distributed GPU environment. And we do this using Horovod. Okay, so Horovod is a distributed training training framework. And we won't have time to explore this, but it's as simple as running it on a single GPU. The only difference is that you just have to use the Docker image, and then you're going to have to just run a simple command, and this will save you a substantial amount of time in terms of training time. The other part that we also did not explore here is the ability to basically run custom models. Okay, so here in the classification example, all you needed to provide is just your model and some parameters. If you're going to go a bit fancier and provide some object detection or segmentation modules, you might need to provide your own eval function as well as your own loss function. And we have a lot of examples on how to do this. And it's also as easy as just implementing a couple of interfaces and then just calling the endpoint with the same exact parameters, plus the loss function, the eval function, the forward pass, if you want to implement your own forward pass. So yeah, that's pretty much it for the demo. And before we get into questions, I just want to let you guys know that we have a references slide at the end. If you want to know more information about how Neutrino works, there's a couple of publications that you can check out, and there's a talk by Hassan, our CDO, on how how do we do our optimization. There's also this basically you can also, as we said, we're probably going to be launching the community sometime soon, late this month or next month. But before that, you can also participate and sign for a basically pre-register for a license, for a community license in advance, and this will be included in the slides. So yeah, that's pretty much it. We're happy to take questions.